Hello everyone, it's a great honor to present our paper, Globe-Bust VP, Convex Relaxation for Robust Vanishing Point Estimation in Manhattan World. This work is led by me and Zhenjun Zhao in collaboration with Haowang Li, Yi Zhou, Yingping Xing, Hao Li, and Peidong Liu. In a 2D image, lines that are parallel in 3D space appear to converge at a single point known as the vanishing point. A space containing three mutually orthogonal sets of parallel lines is referred to as a Manhattan world. Vanishing point is a fundamental concept in 3D vision with broad applications such as structure for motion, simultaneous localization and mapping, camera rotation estimation, and structural understanding. In this work, we address the problem of joint vanishing points estimation and line labeling. From a single image, given a set of unlabeled line segments and the camera's intrinsic parameters, our goal is twofold. First, to correctly assign each line segment to its corresponding VP or to an outlier class. Second, to estimate the locations of each VP. In this paper, we evaluate each method according to the following criteria. Global optimality, the solution must be globally optimal. Efficiency, it must be computationally practical. Outlier robustness, it should handle outliers reliably. Generalization, it must work across diverse datasets. One popular category of existing methods follows the random sample consensus paradigm. These methods iteratively sample minimal sets of lines, hypothesize a VP, and count inlier support. This process will be performed multiple times. After that, Ransack will select the vanishing point hypothesis with the most inliers. While Ransack is efficient under low outlier ratios, its runtime significantly grows as outliers increase. Most importantly, Ransack is non-deterministic, meaning there is no guarantee it will find the globally optimal solution. To achieve global optimality, another class of methods employs branch and bound algorithms. It contains two critical steps. The first is the branching step, where the problem's feasible solution space is divided into smaller subintervals. And the second is the bounding step, where it calculates upper and lower bounds to discard the non-optimal intervals. By iteratively applying above two steps, BNB gradually reduces the solution space until the global optimum is found. In contrast to the probabilistic nature of Ransack, BNB performs a deterministic search over the solution space, which can theoretically guarantee the global optimum. However, its major drawback is the computational complexity, making it impractical for scenes with many lines or high outlier ratios. More recently, some research used deep neural networks to directly regress vanishing points from an input image. These methods are often highly efficient and perform well on in-distribution data. However, they lack theoretical optimality guarantees, and their performance often degrades significantly on unseen or out-of-distribution datasets. Our method Globe-Bust VP is designed to overcome the trade-offs in previous approaches. It's built on three insights. Problem reformulation, we first reformulate the hard line to VP assignment into a continuous constrained optimization problem. Convex relaxation, we relax the non-convex constrained problem to a convex semi-definite program which guarantees the global optimality. Iterative acceleration. We propose an iterative scheme that decomposes the full SDP into smaller subproblems, dramatically improving its efficiency. Through these three insights, our method satisfies all four critical criteria introduced before. Let us begin with the first insight. Given the problem of joint vanishing points estimation and line labeling, we find the core difficulty lies in how to represent the discrete labels. Our core idea is to introduce two continuous constraints. The first, a quadratic constraint, enforces every label to be either 0 or 1. The second, a linear constraint, ensures each line to be associated with only one vanishing point or the outlier class. Given all lines, we can collect all the labels into a permutation matrix. Consequently, we can get the corresponding matrix-wise constraints. Next, we construct a distance matrix where the top three rows represent squared distances from each line to each vanishing point. The bottom row denotes a maximum inlier threshold, representing the penalty cost of assigning a line with an outlier label. The objective function is the inner product of the distance and permutation matrices, which sums the distance entries wherever the permutation matrix has a value of 1. The overall primal problem formulation includes three key components. First, the objective function, as we just discussed. Second, the matrix-wise constraints on the permutation matrix. Third, the Manhattan constraints on the VPs, which enforce their mutual orthogonality. With such insight, we can successfully reformulate the hard assignment problem into a continuous constrained optimization problem. As a preliminary step for Insight 2, we lift the variables of the primal problem into a higher dimensional space. This leads to an equivalent formulation, quadratically constrained quadratic program. However, this QCQP is non-convex. As shown here, non-convex problems often contain multiple local minimas. To overcome this non-convexity, we apply a powerful technique, which can relax the QCQP to a convex problem. First, we construct the Lagrangian dual of the QCQP, which gives us a convex dual problem. Next, we take the dual of that dual problem, arriving at the final dual-dual formulation. This transformation is known as convex relaxation, and the resulting dual-dual formulation is actually a convex semi-definite program, or SDP. This SDP can be solved globally using any off-the-shelf solvers. A critical property is that if the relaxation is tight, the solution of the SDP is exactly equivalent to that of the original NP-hard problem. Through convex relaxation, our method not only guarantees global optimality, but can also handle a large proportion of outliers. Although the SDP formulation guarantees global optimality, solving it with all lines and all VPs simultaneously can be computationally expensive, especially in large scenes. Our third insight addresses this challenge through an iterative acceleration strategy. Instead of solving one large SDP, we estimate VPs one by one. In the first iteration, we estimate VP1, treating all other lines as temporary outliers. In the second iteration, we remove lines assigned to VP1 and estimate VP2. Finally, in the third iteration, we follow the same procedure to obtain VP3. This iterative strategy achieves a significant speedup, making global optimization feasible in practice. We evaluate GloBust VP on a variety of synthetic and real-world datasets. As shown here, in both subway and building scenes, our method achieves a perfect F1 score and minimal consistency errors, significantly outperforming Ransack and B&B in both accuracy and robustness. We also compare our method with B&B and Ransack under different levels of outliers. In terms of accuracy, our method consistently outperforms both of them. It even maintains high F1 score under 70% outliers. In terms of efficiency, as shown in the runtime comparison under 20% outliers, our method is comparable to Ransack and significantly faster than B&B. We also compare with learning-based approaches such as neural VPs and Parsac on the YUD and SU3 datasets. Our method outperforms both approaches on YUD and achieves comparable performance on SU3. This difference highlights a common limitation of learning-based methods. While they perform well on datasets similar to their training data, such as SU3, they often struggle to generalize to more diverse or unseen datasets like YUD. To conclude, we present GloBust VP, a novel solver for vanishing point estimation that is globally optimal, highly efficient, and robust to extreme outlier ratios. Our code is publicly available as open source to support future research and applications.